The last presentation before the discussion will be by Greg Landsberg about vanishing dimensions and planar events at the LHC.
Thank you. I also would like to thank the organizers. Since I'm one of them, I only would like to thank Lee and Sabine. Sabine actually did all the organizational work for us, so it was really a pleasure for me and myself to be here without doing much work, so thank you, Sabine. And if you thought that you really heard some weird stuff during the last session and it was speculative, the speculative part is just about to start. So what I'm going to talk about now is a fairly new idea, which is fairly speculative, but I'll try to show you that that might be a different way, different paradigm of looking into things, which we discussed many times at this workshop and beyond this workshop, namely the problem is cosmology, standard model, and gravity, which we don't know how to solve yet. So that's the outline of my talk. I'll tell a bit about the hierarchy problem, because that's something which particle physicists talk about every day, not as much as quantum gravity people, perhaps. And then I'll introduce this idea of vanishing dimensions, which is based on the work done with Louis Dai-Chang, Malcolm, and Lehan, and that's the reference. And talk about the various consequences of this idea, namely gravity-induced dimensionality, astrophysical and cosmological consequences, collider phenomenology, and some conclusions. So, just as a historical thing, unfortunately you cannot see anything on this photo. The reason is that it was taken in a nightclub, where the whole idea actually originated at the Heidelberg workshop on extra dimensions and being black holes. And I'd like to thank the organizers for this workshop for creating this nice environment. And the four of us supposed to be in this picture. You can see it on my screen. The camera is not strong enough. Okay. So let me start with introduction of the Gaussian hierarchy problem, which you heard about many times. And the problem is that the loop corrections to the Higgs mass diverge quadratically with the highest scale lambda, which you introduce in theory, making the Higgs mass extremely fine-tuned. And if you take the Higgs Lagrangian and look at various contributions to the Higgs mass, from vacuum polarization, from fermion loop, from gauge-boson loop, and from the Higgs self-coupling, you see that all these loop contributions are divergent as lambda squared. And they all have different coefficients, but the common part is lambda squared. And if you add these together, the typical corrections to the Higgs mass squared is proportional to the lambda squared divided by vacuum expectation squared with some coefficient, and then some combination of various masses of various particles. I only put top quark here because the top loop is the major contribution as the heaviest fermion to the correction to the Higgs mass due to the fermion loops. And if you want the standard model to be the correct picture all the way to the Planck scale, if you put lambda on the order of Planck scale, lambda over that of the Higgs, which is only a couple hundred GeV, is sufficiently small, and when you square this, you get that the fine-tuning at the level of 10 to the minus 32 in order for Higgs mass to be at a few hundred GeV, similar to the depth, and not run over into the Planck scale. That is known as the gauge hierarchy problem. Why is it so annoying? Why these cancellations, we don't like them to happen? Well, the problem is that we know that large hierarchies tend to collapse. That's an empirical thing which we know from everyday life. If you look at this picture, you know it cannot be stable. And unless there is some string attached or somebody's holding something, you know that this human tower would fall. And this is, on the other hand, mechanically nothing prohibits a long object not to be stable. In principle, mechanically I should be able to balance this pointer on its tip. The problem is that I would have to fine-tune the initial conditions so that the projection of the center of gravity of this stick is within the point of the stick. And that requires a fairly high amount of fine-tuning. So practically, if you walk in the room and you see this stick standing on the floor, you know that something is wrong. There's something wrong. And that's why we don't like the hierarchy. Yes, Lee.
Yeah, I mean, a counterexample is the university system.
Okay, well, Since you mentioned social system, the large hierarchies tend to collapse not only mechanically, but socially. I swear I didn't plan this question. So that's one example, another example of large hierarchy which collapsed, and that's a more recent one.
You mean grand unifying theories are not going to work, huh? That's right.
Okay, so that's what's the problem with the fine-tuning. However, we should keep in mind that certain amount of fine-tuning, which is required to keep a large hierarchy stable, does exist in nature. The most well-known example is the solar eclipse. It turns out that the angular size of the sun and the moon, if observed from the Earth, are the same within 2.5%. And it's a pure coincidence. There's absolutely no underlying physics principle why it is so. And yet, due to this fine-tuning of the order of 2.5%, we are happy to see this beautiful natural phenomenon as solar eclipse. If you think that 2.5% is not extremely high fine-tuning, I can give you a less, also well-known but less used example, which is the infamous Florida recount, where the number of Republican and Democratic votes was fine-tuned to unity with 10 to the minus 4 precision. And that again happens, although to the best of my knowledge there is no underlying principle why this number is fine-tuned to 1 to such a high precision. Since I fly a lot, like many of you do, one day I was on the plane and I was typing something scientifically looking at my PowerPoint, and the guy sitting next to me asked this dreadful question, what do you do? Well, there's no good answer to this question, as you all know, so I just and I said, and I tried many, none of them worked. So, and then he said, oh, you're a scientist, so you must know what would happen if I take 9, 8, 7, 6, 5, 4, 3, 2, 1 and divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 8, 9. I said, well, you know, I don't know exactly, it's about 8, so I popped up the calculator on the screen, did the calculation, and the number is 8, only 10 to the minus 8 degrees of precision. So he asked me, do you know why? I said, I couldn't tell you why right now, but I'm sure it's not coincidental. By the end of the reply, I actually figured out why it's so fine-tuned to 8. And among these 3 examples, the first 2 are real coincidence. The third one is an example when fine-tuning, in fact, is due to deep underlying principle. And essentially, the hope of this talk, and my hope personal, is that we should be able to explain the 10 to the minus 33 fine-tuning of the standard model as the third example and not as the first 2 yesterday.
The second is not a coincidence. They stopped the process as soon as the coefficient was greater than 1.
Okay, that may be. Then it should be fine-tuned much more. Right? It should be 10 to the minus 6, not 10 to the minus 4. So I guess there are 100 different districts. Yeah. That's like, whatever, maybe. Anyway, so this last example is not really in numerology, but really there is no other way around, because the only other way around, if you are not going to explain the fine-tuning of the standard model from scientific principle, is to invoke anthropic principle, which for Greek friends in the audience comes from the word anthropicus, which means poor taste. So we have to find a more scientific explanation, and that's what I'm going to talk about. So now let me introduce this conceptually new paradigm I'm going to talk about. And the paradigm is that the effective dimensionality of space depends on the length scale we are probing. At short distances, the dimensions of space vanish one by one. At the intermediate scale we are used to, the space is clearly three-dimensional, no doubts about that. However, we postulate that at scales of the order of an inverse TeV, the space is effectively two-dimensional. And even at higher energy scales, for example, during the Big Bang and after the Big Bang, the space, in fact, is one-dimensional. Conversely, at large distances, the dimensionality of space increases, and at very large distances, space is effectively four-dimensional. And maybe there are higher dimensions as well. So this is shown by this illustration where we go from hypercube to cube to a sphere to a line, and characteristic distances are L2, L3, and L4, and I'll use them through my talk. This is a fundamentally new idea, fundamentally new concept, which is very opposite to the paradigm of large extra dimensions, where totally opposite thing happens. Extra dimensions open up as you go to shorter and shorter distances. Here they shut down. Yes?
That's similar to exponential knowledge, God, or Havas quadratic knowledge.
In a sense, there's some similarity, but there are a lot of differences, and I'll talk about this in detail. So, first of all, how do we cure the hierarchy problem? Why this setup helps us to cure the hierarchy problem? So that's fairly easy. What I showed you was actually the 3+1 dimensional integration over the Feynman path integrals, and in 2+1 space, the divergence of all these loops is only linear because, first of all, the phase space factor is not d4k but d3k, and second of all, the amplitude changes as well. So if you do these calculations in the 2+1 space-time, you get only linear divergences for all three contributions to the Higgs mass. That certainly helps. You don't run into troubles as fast as with 4 dimensions. And moreover, when you go to 1+1 space-time, the divergences actually become logarithmic, which is very good because we know how to deal with logarithmic divergences, and they are